Good to go. Um, Hello, everyone. Thank you so much for coming today. As Jolly introduced me, my name is Hossein, and I'm PhD student at the University of New Brunswick, but I'm visiting a student at Ryerson. So I'm here to present our work on swim stroke analysis. So this is a joint work. Actually, 2 years ago, 2017, Amin and I took a computer vision course and we picked this as a course project, and later we decided to develop it more, and do more experiment and make a publication out of it. And then Howre joined us. Rainer was our prof in the course and also our supervisor in this work. So uh, basically this work at this moment is in the earlier stages, so we want to develop it more and make a hopefully a startup company. uh, the motivation behind the work is very simple. By study from Bradford 2004, majority of people are visual learners, meaning that people learn faster if they see what they are doing, right or wrong. So in a sport, in particular, actually the athletes actually can gain the maximum potential by analyzing the videotapes of their own swim and giving, asking for tips from the coaches by just analyzing the videos. Specifically in sports in which the poses are very important. The poses efficiency leads to the overall performance of the athlete. For instance, in swimming or in tennis or in basketball, where the pose efficiency is very important. For this work, in order to just prove the concept, prove the idea, we choose the front stroke. As you might know, in the front stroke swimming style, we have four main steps to do the hand stroke. The first is the catch, which means that you stretch, actually you rotate your body, and then you stretch your hand in order to enter the water and reach as much water as possible. Next, you have to pull the water in order to create a moving force and move your body forward. So the more water you can pull, the more actually you go forward. The next is the push, in which you push the water alongside your body, and then the recovery phase, in which your hand actually exits the water, and in this phase, actually the swimmer put the least amount of pressure or power because it's the recovery phase for the hand, and instead the swimmer actually must switch the power to the other hand. So these are the main actually steps in front stroke. Uh, Again, for simplicity in this work, we chose the pooling phase. Uh, and there are three main reasons. The first is the pooling phase is the most important phase. As I said, if you do the pooling phase efficiently, you can go faster, you can swim faster. Secondly, analyzing the pooling phase is very simple. It only needs the front view image of the swimmer. So we can fix the camera and ask the swimmer just to swim toward the camera, and then we can analyze the pooling. For the other phases, it needs other angles of the recording. And thirdly, actually, the pooling phase is shared with other swimming style as well. For instance, in butterfly or in breaststroke, the pooling phase is the same. So because of these three reasons, actually, we chose to analyze the pooling phase. In pooling phase, the efficient pose is this. So instead of just defining this pose by words, let's do the visual learning. So this is the high elbow pose, which is the efficient pulling pose. As you see, the upper arm must be maintained close to the surface water, and there should be a specific angle between the upper arm and the forearm. So we pick the alpha and beta angles. And this is my Socrates, our coach in the Master Swim Club at Ryerson. Uh, in contrast, with the high elbow, we have a dropping elbow, which is inefficient. So which means that the upper arm and the lower arm is in line with each other and down deep to the water. So this pooling is not right or inefficient. Um, so now we can compare them. So if the swimmer do this, it is efficient. However, that is the, inefficient one. So I guess the task is right now clear. So basically, we want to predict the pooling efficiency of a swimmer. In another word, we want to build a machine or build a software. Given this image, we want to classify this as an inefficient pooling or dropping elbow. And if we give to the system this image, we want to classify this as a high elbow or efficient pooling. So this way, we want to provide visual feedback to the swimmers. Either the swimmer is doing good or bad in pooling, only in the pooling phase. Then we did some research on literature. In the literature, there have been some works doing some analysis on swimming. For instance, in 2014 and 2017 by these guys, they do a stroke rate actually analysis on the broadcast videos. In these works, they locate the swimmer in the line, a kind of localization of the swimmer, and then just by identifying the elbow of the swimmer out of water, they count the strokes. So basically, they give some indicators or statistics about the stroke rate. These works are not helpful for our purpose because uh, it is true that these works actually gives you some statistics about some indicators. For instance, stroke rate, heart rate, the number of laps you swim or the speed you swim, but they don't help the swimmer in order to fix the pose. They just give you some statistics. But in our work, we wanted to fix the poses of the swimmer. We want to give visual feedback to the swimmer. So just statistics or some indicators is not enough for the swimmer. Another category of the works is this, a work by Zeka in 2017. They do pose estimation. It's very similar to our work in this presentation. But the thing is, they do analysis on the swimmers in the swim channel or swim labs. Here in this picture, you can see an example of a swim, channel or swim lab. Basically, the swim channel is a small swimming pool. In this swimming pool, instead of just the swimmer cannot go move forward. Actually, they simulate the flow of water, and they can adjust the velocity of the water. And the swimmer task is to maintain its body in the middle of the swimming pool. So they done the analysis on the swim channel, and one thing is that these channels are equipped with the 360-degree cameras, so in order to capture all the movement of the swimmer. They build a deep convolutional neural net and then train the model on the labeled data set. And this is very similar to our work, but the thing is, our purpose of the work, actually it's red, this one. We wanted to do the analysis on amateurly recorded videos. The thing is, the stream channel is not accessible to all types of swimmers. The stream channel is for highly competitive swimmers, and you have to pay a lot of money. It's not affordable for anyone. So we wanted to do the analysis in any normal aquatic settings. For instance, in Ryerson swimming pool, you record your video and you want to actually analyze it. Yeah, that's the purpose of our work. But one thing was that this work actually gives us confidence that this analysis is doable. Then we do more searches on different sports, in other sports. For instance, in Taekwondo, there's a work that can classify the kick from the punch from the images. In boxing, they can classify the punches into uppercut, straight, or hook by just analyzing the images of the athletes. But one thing is that in these works, they use the images with the depth information. In other words, they use the Microsoft Kinect. It's a special camera, the RGB plus the depth information in order to detect the joints. Again, these works actually gave us another hint that there are some API that you can use in order to detect the joints. But these APIs are working with the depth information. So we decided to buy a camera in order to record the swimming strokes. with the depth information and use the Microsoft Connect. But then I saw this brilliant work. Uh, it's a work highly acclaimed in the CVPR 2017. The same year we were working on this project. So it's a work by Kao et al. Real-time multi-person 2D pose estimation. Basically, uh, this API can detect the joints from 2D images, so it doesn't need depth information. Another interesting thing is it can do real time, meaning that you can input the video, and on the real time it breaks it into frames, and on the real time detects the joints and the body parts. And another thing is it can do on any multi-person environment, meaning that if the image has 2 or 3 persons, it can detect the joints of each person individually without mixing them. So it's the multi-person part is very actually state of the art. But in our work, because we are analyzing with just one swimmer, so it's not applicable to our work. But the 2D pose estimation and the real time is applicable to our work. And this is the sample. Basically, it gives you the 2D position of the joints in the 2D image. So these are the joints by default can be detected by the API: nose, neck, right shoulder, right elbow, right wrist, and etc. And this is a sample output. You can ask this API to give you the joints of the fingers. I mean, in a finer grain, you can ask for the joints of the finger or joints of the face or even joints of the foot. So, but for our work, we only use the default setting, just the main body parts or joints of the body. So finding this work was a huge relief for our work. So simply we want to record the swimming and then give the video to this API in order to detect the joints and calculate the angles. But there are some challenges. The first is, does this API works fine underwater for this environment? This is the page from the last. This is the last page of the paper. So you see that in any environment, it can detect the body joints without mixing them. Lots of people in any type of environment. And then suddenly, I saw that picture. It gives me the confidence that this API can work underwater. So everything is ready.
Can I ask a question?
Yep.
So what is the data set that that API is trained on? Do you know?
They released the data set in the URL. In this URL, actually the code is available online. And in this URL, there is one thing is this API has a sophisticated documentation. That's a good thing. You can easily install in any platform, CPU enabled or GPU enabled. Enough amount of documentation, and all the data set is released in this URL. Yeah.
But it is essentially, people posing in different environments, or
No, actually, in the training set, they manually label the joints, and then they train the model in that labeled data set. Basically, I can explain the architecture. I mean, later or now.
I think the question is more about how robust it is, like because there is background noise, there is all factors in image recognition that you want to be.
The model actually can be trained on any type of data set. You can.
You train it for your.
No. For this work, actually, we didn't train it. I can explain it that, but the idea of this paper is to work on any environment. But the thing is, you can train it on any specific data sets. I'll explain it more later. Yeah.
Or I can add something. Well, the performance still is a little bit dependent on your training set. So if you train it on, if you want it for underwater circumstances, you provide it with data, with that data. But the data that they have trained on has been good enough for our work. Not superb, but has been good enough.
And another thing is that in this work, intentionally, we didn't want to add anything. We just want to use the bare minimum, the already pre-trained model, just the recording does the streaming. No image processing, no pre-processing or etc. We just want to just package these blocks to each other just to output the result. Yeah. And this is the formal definition of our work. given a video of n frames, which is taken this way. I mean, technically, we align the world coordinate system with the camera coordinate system without any, I mean, translation. The only translation is the z-axis is in the opposite direction. So it means that because when there's a difference between the camera coordinate system and the world coordinate system, you have to do some calculation. Again, we want to simplify that. So we just put the camera in the swimming wall, attach it to the swimming wall, and then we ask the swimmer to swim toward the camera. So the only axis which is different from the world coordinate system is the z. And then we want to classify each frame to these three labels: high elbow, dropping elbow, and if it is not in the pulling phase, we want to classify it as no recognizable pulling pose. So there is still another limitation in this classification. We can talk about that later, but here's the simplest form of the task. So the approach has two steps. The first is extracting the poses. So we map each frame to a d-dimensional feature space. The feature space has two sets of features. The first is the joints, which is done by the OpenPose API. And then the angles between the upper arm and this water surface, and the angle between the upper arm and forearm, which we do by just this simple formula. Probably you know this formula from high school. If you have two lines of slope M1 and M2, you can calculate the angle between these two lines given the slopes of the lines. So again, there's another limitation in this work. It is simple, but there's another, I mean, bug in this calculation. We can talk about this later. But yeah, we calculate the alpha, the beta, and we identify the joints as the features of the frame. Then we train a model. For the detection of the joints, we use the pre-trained model of the OpenPose. We just use the pre-trained model. And then we learn a classifier. So we use the well-known classifiers, random forest and SVM, as two baselines. And yeah, that was the work.
Short and sweet.
Yeah.
I have a question.
Yep. Go ahead.
Can you pick up from here? Oh, okay.
There is a question.
Could you repeat what the input is? The input is like subsequent frames, right? So you do a. I may have missed.
The input is just a frame.
Oh, sorry. I mean, like you take those joints from PoseNet or OpenPose, and then that's one frame. But like, do you have multiple frames?
Actually, we record the video.
Okay.
So then we input the video to the OpenPose. The OpenPose actually breaks it into frames.
Right.
And then for each frame, it gives you the joints of that frame.
Right.
So yeah.
But do you
and
window
then
it?
and then we consider each frame as just one sample training set, one sample in the training set.
Oh, one sample in the training set.
For instance,
Okay.
let me explain it. For instance, this is one frame,
Mhm.
and we manually label this frame because it is the high elbow. So we manually label this as the high elbow 1.
Uh-huh.
So let me show you another slide.
So there may be a subsequent frame which you treat independently as another data set.
Exactly.
That's
Yeah.
the point.
These frames are in the classifier. These frames are considered as distinct samples.
Okay.
Yeah.
I see.
For instance, here, I mean, we have a frame. We classify it as 0,
Okay.
and just the frame. So this video has, I mean, more frames. So each frame actually is manually labeled.
Okay.
Yeah.
I have another question, but I'll ask later.
That's okay. Yeah, kind of thing, because
Can
we
you repeat the
manually label
question?
the high level, yeah, class.
Repeat the question.
Is this a supervised learning?
Supervised.
Yeah, basically it's because it's a classification. Yeah, we manually label the frames. Yeah,
Manually labeled.
yeah, exactly. But about the frames, not the pose detection. The joints are already pre-trained.
What was the threshold? How did you determine between the upper elbow and the straight arm?
Oh, there's no threshold. Because I mean.
So what if the arm is like so? At what point did you decide, oh, it's this, I'm going to classify it as this or this?
That's the purpose of the machine learning. So, for instance, we ask a swim expert, and we give the swim expert all the frames. And the swim experts distinguish between the high elbow and the low elbow.
So it's just the human judgment of,
Exactly.
of an expert coach,
Exactly.
and they would decide at this point I'm going to label
Exactly.
it this way.
And the machine actually, the classifier actually automatically formulate the threshold. For instance, whenever see this angles, it classifies the frame as the high elbow.
So it was just a
didn't
visual
specify.
judgment call, like of your expert.
Yes,
Yeah,
that's
okay.
that's a bug for any machinery. Yeah, you're right.
So you just had like one person evaluate these images, or you had like maybe a.
Just one swim expert. Yeah, yeah. We couldn't actually afford more than that. Actually, later I'll explain. Actually, it's a course project, so we didn't have enough money. Even for the publication, actually, we paid the registration out of our pocket. Nobody actually fund this project.
So, for the input data, back to the previous questions. So, let's say you get all the frames from the video. So you use all of them as a input data, or you select just like a subset of the frames you get from the video.
For the, in order to calculate the accuracy of the model, actually we split it to training and test set.
Yeah, but you use all the frames you extract from the video.
Yeah, you're right. Yeah,
okay.
Yeah.
So that means there will be a bunch of frames, so that the people's pose almost the same, just slightly different, right?
You're right. Exactly. For instance, the immediate frame after this frame is
Almost the
kind
same.
of the same as this. So this is another sample. Yeah, we consider it as another sample. Yeah.
And one, so when do you consider it done? Transition between different poses, because it is in motion. When do you consider it the beginning of the pulling pose and the end of the pulling pose?
You're right. I can show you that. Let me come back to here. As I said, all other poses in this work is considered as -1, meaning that no pulling pose, no recognizable pulling pose. One improvement to this work would be this. We can do the pose detection first. Let's first find the pose. Is it pulling, or is it catch, or is it push? And then decide whether, if this is the pulling phase, let's decide it is high or dropping. But in this work, all other poses are considered as -1. Yeah.
Last question.
Go ahead.
So you mentioned that for the open pose, you just used the pre-trained model.
Exactly.
And you mentioned that the performance of it was sufficient for your specific project. How do you determine it was sufficient?
Sufficient. I can actually I leave them after the break, so I have more slides. In the result part, I can show you some false detection under the water, and that's why we want to develop it. Because first we have to make a huge amount of samples, and then we have to ask, expert to manually label the joints, and then train the model. So this is another phase. But the paper in the open pose actually claims that it is doable. So we want to train the same architecture but in different data set, and then probably it improves our results. Yeah. Go ahead.
So when the expert is labeling all the photos, is he doing it sequentially frame by frame, or did you shuffle the photos?
Actually, we give the let me remember.
I'm just curious if he flips through all the photos. Can he see the motion?
First thing we did that I can show you a sample. Video frame. The thing is, because the swimmer actually starts swimming from the other wall, so up to some point we do not have any pose. So there are lots of frames that there is no joints. So we did. We start from the moment that we have at least one joint detected. So I'm sure that we just remove those frames, and then I don't remember how can we manually label that. But yeah, there's only one swimming expert. It's 2 years ago. I don't remember. Sorry.
It is very probable that the frames have been shuffled. So So the swimming expert does not sit like this and see all the frames of same person to the end, and then let's go to the other person.
But the thing is, because another thing is, we wanted to do it quickly. So the thing is, that's why I'm not sure. Because as our friend says, because the moment, I mean, 2 or 3 frames after this frame is classified as high elbow, so it's easier for the expert to manually label this frame. But imagine we shuffled all the frames of all swimmers. So when the expert see this, label it as high elbow, another frame would be completely different frame. So it takes at least 1 second to again judge it whether this is high or dropping. So, but if they are sequential, the labeling is faster. That's why I'm not sure, but I guess we didn't do any shuffling, something like that, because of doing faster labeling. Yeah.
There's a question from online.
Yeah, there are 2 questions, but the second one I'm going to defer out to the second part. But this question doesn't make too much sense to me. I'm just read out loud. How did you make sure that the frames are not shuffled and are in order if you skip the video processing? Exactly.
Say it again, sorry.
How did you make sure that frames are not shuffled and are in order if you skip the video processing?
The frame has numbers. Actually, for instance, let me show you in the. I hope I can have it. Actually, we have a sample data set. Actually, we couldn't release the data set because we doesn't have that consent because the swimmers ask us not to release their body in the public. But I put my own swimming, so.
You're broadcasting your desktop to the.
No, it's just, as you see here, the frames has numbers. So these numbers, for instance, 839. Let me open. Oh, this is very close.
This is
Oh, let me show you. I guess this is better. For instance, yeah, for instance here, these frames has numbers, and for this frame number, the open pose actually output an XML, the poses. Here, the JSON for that frame. For instance, that frame was, for instance, this frame. So you have the poses of that frame. So these are mapped to each other. So we put this, in an Excel file, and the expert actually opens the file and label it as 1 or 2. Later we map the 1, 0, and -1. Later we map that number of the frame, the expert actually labeled it as 1, 0, -1, to this pose. Yeah, that's simple. I can show you the XML of the labels as well. So, because you already, for the conference, we already published the code. So, sign up sheet, data is, yeah, here is the Excel sheet, the poses, and I guess the last column is the label. Yeah, manually label. So the expert says that this frame is 1, 0, or -1, and then we put that label to the pose. We map that to the pose.
What's the percentage of 1 minus 101 in your training set?
I guess I put it in the paper. Can I see? Sorry. Yeah, the no pulling pose is 48%, which makes sense, meaning that that's the recovery phase, etc. But the thing is, whenever the other hand is in the recovery phase, the other hand is doing the pulling. Not necessarily, because sometimes we have this, but this is makes sense. This makes sense. The dropping elbow is 38%, and the high elbow is the 30%, because all the strokes of our coaches is considered as the high elbow. At first, we decided to label, without any expert, we wanted to label all the pulling phase of all the swimmers in the line 3 and 4, because in swimming, the line 3 and 4 are for professional swimmers. So we said that we don't need any expert to manually label the frames. Let's consider all the frames of these swimmers in these lines as the one high elbow, and the other lines as dropping. But this is not true, because there are some swimmers in the line 3 and 4 that they do dropping. And the thing is, in the past, about 20 years ago, they believed that the dropping elbow is the efficient one. Nowadays, they prove that the high elbow is the most efficient one. That's why, the old swimmers actually is still doing dropping elbow. Yeah, that's the statistics in the paper. Yeah. Thank you.
All right, thank you everyone. So we're going to have a 5 minutes break. There's more pizza if you want to help yourself. And after the break, he will actually review the results, and then we'll have more discussion.
Good. Hope you enjoyed. I mean, the work. Before I go forward, I just want to ask you a question. What's the most challenging step in any machine learning data mining task?
Data collection and labeling.
Exactly. Exactly. You know, that's the most, I mean, challenging and the most effort actually in any machine learning. So let's start with that part. For the data set, actually, we have to do the underwater recording. So, and we intentionally didn't want to use any sophisticated camera. So I had an iPhone 6. So iPhone 6 is not waterproof or water resistant. So I searched on YouTube, and there was an idea. Let's put the iPhone 6 in your Ziploc, in a Ziploc. So I tried that, and it worked fine. So, but something happened to my phone later. I'll discuss that. Because of that incident, we had to use, we used the iPhone 7. iPhone 7 is claimed to water resistant in normal water, not in, swimming pool because of the coloring and etc. But still, we did the whole experiment with the iPhone 7. As I said, front view recording of the swimmers. Actually, Negar was our lab mate. Still, she's our lab mate. We borrowed her phone, the iPhone 7. Actually, nobody dared to borrow iPhone 7. At the time, iPhone 7 was the brand new phone. So we asked her to borrow. Actually, she borrowed her phone to us. We did the experiment, so we have to acknowledge her right now. Yeah, sure. Yeah, actually, she is doing great at our lab. So yeah, we highly appreciate her for that. And yeah, that's the sign up for the swimmers. Actually, I'm a member of the Master Swim Club. So I went there and I prepared this sheet, sign up the swimmers. And as you see here, we have a fair distribution of the swimmers over the different levels: fast, faster, or fastest, or beginner. I mean, I don't know, beginner, what's the next step, and the professional one. Different genders, male and female, different body shapes or size, large, medium, double X large, and etc. But the thing is, in the age, most of the swimmers are 30 or 40 years old. So that's the disproportionate actually distribution. But about other factors, we have a fair distribution. Just to show that this analysis is not biased toward any body type or body gender, etc. And we have to thank actually Danica. Danica is the head coach of the Master Swim Club. So she permitted us to do the experiment in the swimming pool, and all the members who actually participate in this experiment. And here's the result. So we have two classifiers. In each classifier, we use the different sets of features, the joints, angles, and both features together. As you see, the best result is for the joints and the angles. And also, comparing the random forest and SVM, random forest always actually doing great comparing with other classifiers. And this is the setting. The result is based on the stratified tenfold. Because we use the three classes, so we report these values based on the weighted average. And this is the platform, Core i7 quad core. The open pose actually runs faster if you have a GPU enabled device. So we use this NVIDIA GeForce 1070 with 1920 GPU cores. Yeah, this is the experimentation setup and the result. But these results just show the accuracy of our model or analysis. But this is not useful for the swimmers. For the swimmers, this map is considered as a visual feedback. For instance, here in this picture, we have a frame number 100 to frame number 200. So these are the frames. And the predict, yep. Oh, sorry. And the predict, Ola, you're right. Oh, yeah. The predicted actually values are blue circle. So these are the predicted value of the classifiers. The true value is the red square. So you see that this 66% accuracy actually there are some errors. you see. But the thing is, imagine we have a, perfect classifier, meaning that all the true values and the predicted values are completely aligned with each other. So if the swimmer, all the pooling poses are, all these points are in this line, meaning the classify 1, which means that the high elbow, it means that the swimmer is doing right, high elbow. There would be very few points in this line, which means that the dropping elbow. In contrast, if a swimmer has lots of points in this line, meaning that all the frames are classified as the dropping elbow, and there would be very few points in the high elbow, meaning that the swimmer is doing bad or is doing dropping elbow in inefficient pose. And so this, I call this swimmer pooling map. So this is a feedback for the swimmer. Actually, it gives an idea to the swimmer that the swimmer is doing dropping or high elbow. And this part actually shows some false detection. As we discussed, for instance here, because of the water reflection and etc., the pre-trained model of the open pose actually detects another individual in the water. But the swimmer is here. So we didn't do any image processing. For instance, we could crop the image just to focus on this part of the image. Also, we can train the open pose on our labeled data set just to bypass these, individuals. So probably if we train the open pose on our own labeled data set, we might improve the model. Another interesting thing is this. The open pose, using the pre-trained model, when the swimmer is far from the camera or very close to the camera, there are lots of false detection. But in a specific, distance to the camera, the open pose works, perfect. So another factor is this. What's the perfect distance of the swimmer to the camera in order to classify the pooling pose? So there are two options. We could improve the model in order to fix this. When the swimmer is far from the camera or very close to camera, or instead of just fixing the model, just detect the perfect distance of swimmers to the camera and then do the analysis. And we have to thank actually Dr. Ali Rezai. Actually, we didn't have enough money to buy a platform to do this experiment. So we communicated with him, and he gave us access to his lab, GPU workstation. All that software platform is supported by the Dr. Ali Rezai at Ryerson. And yeah, the takeaways. Actually, the takeaways, I couldn't understand the S word, but for me, the takeaways of this project are these. For you, I don't know. But for me, I lost my phone. So actually, at the time, I bought a brand, just the year before this project, I bought a brand new phone. I put my phone in the Ziploc, and then I asked the swimmer to swim toward the camera, and then I put the Ziploc underwater, but I forgot to zip it. So, and one brilliant takeaway is this: no pain, no gain. So it's not easy. So, and another actually upsetting thing is that I got B in that course. I expect to get A minus at least, but I got B. So it doesn't matter for me. Actually, I just wanted to prove the concept. I want to just prove that this is doable. And later, actually, I did a pitch on RBC competition at UMB, and I won. I become the third place, and I won 500. So it's yeah. I hope you have, good takeaways from this presentation as well. And now the discussion point. So I guess we already covered most of these discussion points, but yeah, I don't know how can we manage the discussion point. I have to read it and then.
So
Okay.
I can either read it or you can just read it and read through. I think we just covered a lot of them. You can just read and
Go ahead. Yeah, sure. Actually, we can discuss this. These are just, future works or some more points to discuss in our work. Uh, the first one actually we already covered. I mean, in this work we didn't do any pose detection, so we consider the catch, recovery, and the push phase as -1, meaning that the no recognizable pulling pose. Uh, it might be better to first detect the pose and then do the analysis. So as a later work, it might improve the accuracy. Another thing is that this one, uh, in our work, actually, it's a classification. So classify as a high elbow, dropping elbow, or -1. But the thing is, the idea is the visual feedback for a swimmer is the similarity of the swimming with a best one or with the gold standard. So a swimmer records his or her own video and wants to compare his swimming or her swimming with, for instance, Michael Phelps. So we didn't use any similarity metrics. The only similarity we used was that swimming map. We just wanted to show that how many of your pulling pose are high elbow or dropping elbow. But later we have to find a similarity. So we want to show to the swimmer that how close you are swimming to a champion. And this actually, yeah, end-to-end model. I guess building a new convolutional neural net just to do this swim analysis, I don't believe in that. I just want to use kind of reuse the already built, architecture. So I prefer to use the open pose, but train on our own data set instead of just building my own model. So yeah, building an end-to-end model, I guess it's not worth it. And yeah, in this work, we intentionally avoid any image processing. So we just want to show that with the bare minimum hardware and software, what's the accuracy? We got 66. It's evident that if we do some pre-processing on the images, for instance, eliminating the background, eliminating the water reflections, and etc., it actually improves the results. Yeah, we knew that, but yeah.
Okay, so you've already seen the image data, and you know what it contains. We already know that it is a frame of someone swimming underwater. Okay. Do you think it would be such a difficult image processing task to just to detect the like the elbow and to detect the whole arm? Would it be that difficult?
The thing is, we haven't tried other swimming pools. For instance, the aquatic settings may have different settings. For instance, in Master Swimming Club in Ryerson, the swimming pool is blue, and it's indoor. If you want to extend this work to outdoor swimming pool, so it's not that easy. We cannot, assume that all the environment is the same as our images in this data set. So yeah, at first it might be easy, but in practice, I guess we have to explore different swimming pools, indoor, outdoor, and doing image processing. It's fairly, difficult, I guess. Yeah.
So, where do you think currently the bottleneck in the performance is? Is it the performance of OpenCV or the lack of image processing? And where do you see the best investment moving forward to focus on image processing or looking at open photos?
Actually, the image processing is not costly, so doing some very little image processing actually I believe, I assume that greatly actually improves the results. So first, this next step for this work gonna be the image processing. Another step is the training the open pose on our own label data set. But the thing is, right now in our data sets, all the swimmers are from just one environment, as I said, in the Ryerson Swim Club. So we have to explore other swimming pools in order to have, fair distribution of the images in all aquatic settings. That's the next step. So yeah, a special type of training on our data set will improve the work, yeah.
I have a question online. It's been queued up for a while, so I'll get it out. On page 3 of the paper, does anybody have paper?
Yeah.
The feature vector seems to contain the joints and joint angles.
Yeah.
Why isn't the energy expanded per combination of joint and joint angle included?
Why they what?
Okay. Why isn't the energy expanded per combination of joint and joint angle included? Since the goal is to expand less energy per stroke.
Like in joules or something, measuring energy expenditure in joules based on the swim stroke, where you are in the swim stroke.
As some extra features.
Yeah.
The energy of the pool.
Oh,
yeah.
I see.
That sounds like a
I
comparison, like
see.
a suggestion.
Oh.
So.
How can we calculate that?
I think one way you could calculate that is having a suit that would measure pressure.
Yeah, but consider this. I have to build that thing.
Oh, yeah.
You may need more budget.
This leads into a question I had, which was, if you had unlimited budget and at least 2 years' time, what things would you incorporate to get a more accurate expenditure of energy for the maximum or the most efficient stroke?
You mean if I have unlimited budget?
And also limited time, yeah. Like if you had all the budget and all the resources you need,
to improve the accuracy or improve the accessibility.
Yeah.
I would work on the accessibility. For instance, we were talking about the idea of feedback on the spot. For instance, I can build, this idea was from Alex. I can build for instance, a suit, as you said, and then when the swimmer actually do the stroke, on the spot, I can analyze the pose and then give visual feedback to the swimmer. In the meantime, the swimmer actually swims. So make it online. So then you do the one stroke wrong, and then you give the feedback. You do the other stroke right. So I would do that. Yeah, if I have unlimited budget. But instead of just improve, because for me, the accuracy of 70 or 80 is enough.
I had a comment there.
So I noticed that after the pose extraction step, you did some feature engineering manually, right? So based on the pose points, you pick up several features, right? You calculate and use them as the features. Then you apply random forest, etc. on it. So I was wondering, so when you do the feature engineering, so it's based on your domain knowledge. Some people told you only those few features can dominate this class, or you just based on your experience you selected those features. I just curious whether you think you may miss some key features when you do this feature engineering, then you apply machine learning algorithm on it. If you don't have domain knowledge or you don't have confidence on your feature engineering, is it possible after you extract those kind of pose information, you throw them to a neural network, let the network figure out the features? Yeah.
You're right, because I had the same idea as you when I did the experiment. Let me show you this. In the result set, I just wanted to put the joints, only the joints, and the joints is detected by the, put the joints, and the joints is detected by the open pose. So there's no feature engineering. All the joints detected by the open pose is inputted to the classifier. This angle is the hand engineered features. So because of my prior knowledge, I knew that the angle must be this, and the high elbow is this position. But it increased the result, improved the result.
If you add more features, does it have? May it have? For example, what I'm curious about, so when you do the swimming, your shoulder level, left and right, so there should be in the same level, or what kind of angle is the best one? I didn't see that in your feature.
You're right. For instance, yeah, you are Definitely right. Let me show you the picture. In our experiment, I saw that. For instance, here. For instance, here or here. Oh, let me show you again by this. Sorry. Uh, we found that the nose actually gives us the how straight is the body. Uh, but still, these. I mean, that's why I was trying to just put all the joints detected by the open pose without any, I mean, calculation. Uh, you're right. We have to try that. Yeah, you're right. For instance, here, although we know that, I mean, this is the right hand, but still we have the, I mean, the rotation. So if the rotation is better, the pulling is better. So these are more features. Um, but you're right. You're right. I mean, these features are hand engineered. We knew that this feature actually has a positive effect on detecting the pulling pose. Yeah. But actually, you put on a very important thing. There is a bug calculating this. Let me show you. Does it move? Sorry. There is a bug calculating this angle. This angle. You know, I knew that, I mean, the angle must be, for instance, alpha and beta. For instance, the beta is 110 something and alpha is kind of 60 something. But the thing is, when the swimmer actually do the high elbow or any, I mean, pulling pose, because the image is 2D, but the action in real life is 3D. So you might, let me show you this. You might do this, and then you do this. It's still you're maintaining the same angle, but in the 2D image, the angle is different. So calculating this way, the angle is not right. You have to consider the 3D version of the angle. There are some method. There are some method that they do calculation based on the 3D angles.
You just said, sorry to interrupt. You just said that, well, you did say before that in the pose detection they're using depth information. I would say if you just feed the classifier that information, it could help. And as you probably know, like there are CNN-based models that have used 3D convolution. So you can use more channels to include depth information as you go on and have just one,
You're right that we don't want to, we don't want to make a recording device sophisticated because we want at the end of the day, you want to any normal swimmer record the video. I guess there's some works that they can, they can measure the angle from the 2D images, but by analyzing the depth information. Yeah, I know that there are some works.
Yeah.
So, question. So, if you applied this to an infinity pool where the swimmer is fixed in three-dimensional space, then you can include that difference based on the distance from the front of the stroke or the beginning of the stroke to the end of the stroke, right? With some level of consistency.
Say it again, sorry.
So if the swimmer was in a fixed point in space using an infinity pool and you had a simple image in front, then you could make a more accurate prediction that the stroke is efficient. Yes? Because here you're measuring a swimmer coming at you. They're traveling, right? But if the swimmer is fixed in space, like in an infinity pool, then the accuracy would go considerably higher.
Oh.
Yeah.
Well, the
like in the swim channel.
Yes, a swim channel. Yeah.
Yeah, like
that's
swim
right.
channel.
Yeah.
One thing actually.
Oh, scale
I received a video from a swimmer that they put the camera with a handle in front face in the front of the face of the swimmer and move walk toward. In that way always the distance of the swimmer to the camera is the fixed and the accuracy is high because the distance to the camera is a factor.
How much more accuracy do you think you could get based on what you had 60-something percent? 66%. Yeah. How much more do you think you'd get?
I don't know.
Just guess off the top of your head.
I don't know.
I think it would go up to at least 80%. especially if you account for the distance from the beginning of the stroke to the end of the stroke.
I mean, especially, I mean, we can use all the frames as the sample set because the fixed and the frames are, I mean, the quality of the frames are high.
Mm.
They
You
have
should
more
at least get like
samples.
85, at least 85%, right? If
That's-
those things are fixed, the variables are fixed, yeah.
There's no guarantee actually. It's
No?
all it's all the dynamics of the data set. You never know.
Mm.
Could you show the results meanwhile? Because we are talking about the results.
Oh, sorry.
Thank you.
But I have to try that. Yeah, that's yeah, the false detection gonna be very low. Then
Oh, okay.
the accuracy is high.
Should go higher,
because there is no false detection.
Right. Okay.
There is no -1. The last, I guess this is the last one, yeah. The last is it possible to extend this work to other sports? My idea is yes, because in any sport that the pose efficiency is important. For instance, my sample is the tennis. In tennis, doing the serve actually is the pose is very important to doing the serve. So my next step gonna be try on tennis, because the recording is very simple. You just ask just put the camera just beside the tennis player and then ask to do the serve. Or you can capture the live video of the tennis players and then capture the joints, calculate the angles, and then compare with the other tennis players. In other sports, I'm not familiar with, but the next step in the swimming is the breaststroke or the butterfly, because the pulling pose is very the same as the front stroke. Yeah, that's the extension to our work.
Okay, I have a question on the algorithm. Maybe I missed it. So, if I remember, like open pose, the output of open pose is like something like a bunch of key joints plus a confidence score, right?
You're right.
It gives a confidence score. So, do you have a cutoff point for each of those?
We use the default setting. We use the default. The thing is, it gives you the confidence score for each.
Default is like 0.5 or something, just something uniformly for all joints.
But I have to see the code.
Okay.
I have to
so
see
it's
the
whatever
code.
output. So the output is then in that case there's a threshold and it's binary. So either
Yes,
yes or no. Okay.
yeah. And the number of people in the image also there's a threshold on that because it detects multiple person.
Okay.
And also for each joint there's a probability score. And actually in the image the color of the joint in the UI shows the score. The more actually it's bright, it means that the more confidence it has.
Okay.
But in the JSON file, it gives the score. But I'm not sure. It gives you all the values, and then you do the threshold, or you can set the threshold, and it gives you all the values more than that threshold. I'm not sure about that.
So by default, when we kind of examine by the eye, usually the result is pretty like on point. Like there's no misclassification. It's just like sometimes it misses a few joints.
Yeah, you're right. Yeah, as I said, as I show you, the more you're close to the camera or the more far you are, the lots of
those weird angles. Okay.
Yeah. Can I just play a sample, because that was the first moment actually I could run the open pose, and I was kind of excited because if this doesn't work, the whole project actually was gonna be failed. So this is a Stephanie. This was the first moment I tried the open pose on the. You see some false detection, and number of people is over there, so it detects this guy. Some false detection. Yeah, at this moment, actually, I was so happy. Yeah. The legs, there are some false detection about the legs and etc. Yeah.
But you don't care about the legs, right?
No,
You don't, okay.
we don't care. Here, Stefan actually when do the pulling pose, at the end, the angle is different. So, yeah, that's a sample I just wanted to show you.
It's cool.
Go
I
ahead.
have a question. So actually, did you choose only the joints for the arms, or because I don't believe the rest of joints are important.
The
Arm and the head only actually. So.
Yeah, just the shoulder, the elbow, the wrist.
And what about the rest? So you.
No,
You don't think so?
No.
And as well, so how important is to use both? So I believe this may be classified as an image classification only. You have just a movement of right hand and left hand, and actually a background or whatever else. So this is a three-class image classification problem.
You're right, yeah. It could be considered as that. Just given an image, a frame, we detect the pose, the joints, and then
No,
as
without
a
detecting
feature.
those. You just have an image input as to CNN and classify this as
High elbow or
yeah.
dropping. Yeah, it's kind of an end-to-end framework. Yeah, you're right. Yeah, you could do that. Yeah, you're right. Yeah.
Okay, thank you for your great presentation. It was really interesting. And I have a question regarding the distance of swimmer to the camera. I think it's an important feature. Why didn't you consider it as a feature? Then you could, study doing feature engineering.
You're right. You're right. Actually, we could fit the frame number and consider it as the distance.
Yeah.
Yeah, you're right. We didn't do that, but we can consider it as a feature.
Sorry, how is frame number correspond? How does it correspond to distance?
Because the frame number counts from 0 to some numbers. So the more the swimmer actually get closer to the camera, the frame number goes high. So it might hint the distance to the camera. So in order to capture the distance, you can rely on the frame number.
When they're getting away? So you don't care about when they're getting away from the pool, like from the.
We stop the recording after. As you see here, when the swimmer actually reach the camera, we stop the recording. Yeah.
So you don't.
But in that case,
so you don't capture them, going away from you at the beginning.
No, just on the other side.
Towards you.
Yeah, just one.
So another point now that I already interrupted you. So you seem to have a sequence of images, right? Which you seem to classify separately, taking no information from like the image before. Is that correct so far? So you're using SVM. You're not feeding it any information from the previous frame when classifying the current frame.
Yeah,
okay, so you're missing the context there, right? So a couple of things that you can do, even with the classical image classification, you can use methods like 3D. Well, also methods like 3D, Hawk 3D, to get both the. So that I think that could also, to some extent, deal with the issue of classifying. Well. Detecting like classifying poses that aren't there, with a holistic sort of view as well as your local view. So both the local and global view that can help with that. Also, as I said, feeding in information from previous, maybe one after or one before frame. Just get some features and put it in at the simplest case. More sophisticated, we can go with more, RNNs that inherently feed in information from previous
You're right.
states.
Yes, you're right. Because the classifier doesn't know that. As a global context, we knew that this swimmer is doing great at the first, and then sometimes doing bad, etc. So yeah, we lose the context. Because for the classifier, it doesn't matter. This is a frame of the same person or another person. You're right. We lose the context. You're right. Yeah.
But it was a class project after all, so
this
is amazing.
This idea actually helps to calculate that angle as well. Because there are some works that they can create a 3D image from sequence of 2D images. So then it helps to, oh, I see.
Yeah, I had another idea for there too. So you have, if you're using just one camera, if by any chance you could use just another camera, get two different angles, then you have, I have to sit down and write the math to confidently guarantee, but I can say to a high degree that it will increase your angle accuracy because there's less chance for you to get it wrong now. If you use it from one angle.
I agree. The two cameras, and the other thing is when they film us, they move the camera. So the coach always has the camera on a waterproof bag that you can get at a scuba diving store, no Ziplocs, and it's on a stick. And she moves on the deck. We're always at the wall, and the camera moves with us.
I see.
And you'll see in the Olympic footage, of course, the cameras are all mounted and they move with the swimmers.
The thing is, one thing, actually, I'm not expert in image processing or kind of thing because my expertise in text mining. So this was a course project in computer vision. So my knowledge of image processing is just, just computer vision. So I just read some papers about image. And the thing is that in that course, when the camera actually moves, it's called action recognition. Action vision. Yeah. Oh, sorry. Active vision. Active vision. Active vision is, when the camera coordinate system is moving, and usually processing images when the camera is moving is difficult. That's why we simplify this project just to fix the camera, just to have it, align the coordinate system of these two things, both coordinate system and the camera coordinate system. That's why we avoid moving the camera with the swimmer. But I guess if you move the camera with the swimmer, still it can be considered fixed because they are aligned with each other. So you can do the analysis simply. Yeah, that's our another thing. Just moving the camera in front of the swimmer. We haven't tried that. But definitely we have to. Yeah.
And you could do it on a budget.
Yeah. The idea was that we wanted to do the same way as a normal swimmer wanted to do later. For instance, the idea is that the swimmer actually do the recording and then upload the video to us, and then we do the analysis automatically. So we wanted to do the same as the normal swimmer do. Yeah, that's it.
I think one other practical consideration is that this entire thing, open pose right now can be shrink down into a very small size with just special like mobile net and all that, and then toward the end you have SVM or some very simple model. This entire thing can be fit into a phone. So I think there's benefit for you to basically just record in the phone and process in the phone, and you don't even have to
just
upload
write
to the
it.
cloud.
Yeah, just write it. Yeah, that's on the spot. Yeah, it makes it, instead of being offline, make it more online. Yeah, that's awesome. Yeah, that's a good idea. Yeah, that was it.
Amazing.
You're
Thank you so much. Thank you, Hawre, for coming with us. This is great discussion point. And thank you, everyone, for making us have another great session. Don't forget to get your ticket tonight because there are only 5 left. And